I guess we can get started. Hi, everyone. Welcome to the C3 AI DTI seminar series for the fall semester. My name is Gauri Joshi. I'm an associate professor at Carnegie Mellon University, and I'm co-organizing and co-hosting this semester's seminar series with Professor Richard Zhang, who is an assistant professor at the University of Illinois. Before we begin, we would like to pause to acknowledge the support from our academic and industry partners, for which we are deeply grateful. Our fall 2022 series is organized around two special themes, adversarial machine learning and distributed and federated learning. And our talks are scheduled to alternate between these two themes. We have some really exciting speakers lined up over the course of the semester. Just to give you an idea, over the next few weeks, we will be hearing from Zico Coulter and Eric Cheng from CMU, and Tom Goldstein from the University of Maryland. And our series will extend all the way to December. You can find the details of the speaker information and abstracts on our website. Also, videos from previous talks, both from the current series as well as past series, will be available on the YouTube channel. So today, we are very happy to welcome Dr. Brendan McMahan to share his research with his talk entitled Federated Learning with Formal User-Level Differential Privacy Guarantees. Dr. McMahan is a research scientist at Google, where he leads efforts on decentralized and privacy-preserving machine learning. His team pioneered the concept of federated learning and continues to push the boundaries of what is possible when working with decentralized data using privacy-preserving techniques. Previously, he has worked in the fields of online learning and convex optimization and reinforcement learning, and he received his PhD from the computer science department at Carnegie Mellon University. So without further ado, let's welcome Brendan McMahan. The talk will be about 50 minutes. And for the audience, please use the Q&A feature to submit your questions. We will ask them on your behalf at the end of the talk. So let me stop sharing, and Brendan, you can take over and start when you're ready.
Great, thank you so much for the
We are not able to hear you.
Now can you hear me?
Yes, now it works.
Yes, I think my slides stole the audio, but my slides don't have their own audio, so that wasn't very useful. All right, and you're seeing the slides?
Yes, we can see the slides.
Great. All right, let's get started then. So yeah, I'm going to talk about federated learning with formal user-level differential privacy guarantees. If you don't know yet exactly what federated learning is or what differential privacy is, don't worry, I'll get into all of that. And even though I'm presenting this, I want to be very clear, this represents the work of very many people at Google and many collaborators beyond Google as well. This is an area we've been working in for a while, and I wanted to go back to some of the original and ongoing motivation for this work. And one of the first observations is that increasingly data is born at the edge. So we have billions of phones in the world, IoT devices, and they're constantly generating data, both from digital interactions, but also from real world sensing. So think about cameras and microphones, GPS, accelerometers, all of the sensors that are packed into modern smartphones. And that kind of data really does enable better products, smarter machine learning models, and so on. And there continues to be tremendous untapped potential there as well. And so, one of the trends we're seeing is that there's a lot of reasons to want to move the processing of that data onto the device and keep the data on the edge. So improved latency, experiences that work when you're offline, better battery life, and certainly privacy advantages. So on-device inference and mobile keyboards and cameras is one notable example here. But really, developing these products and services, certainly doing machine learning, is a closed loop process with data. And so if the data just stays at the edge, which we think is necessary to kind of utilize that data as much as possible, how are we going to do analytics? How are we going to do machine learning? And so those are really the questions that motivated the initial work we did on federated learning. And so here's kind of a cartoon overview of what a federated learning system looks like. In the cloud, you have an engineer who wants to do model development, but instead of having the data in the server, the raw data is on client devices. And so they run some kind of iterative computation that sends, say, the current model down to those devices. The devices do local processing. And then eventually a final model is trained. That's maybe released to the model engineer. They do some evaluation on it. And if the model is good enough, then maybe it's shipped out to all user devices to be used in an application like Gboard or other Android services. So what makes a good application of this flavor of cross-device federated learning? The best applications tend to have the properties that, first of all, that on-device data is either more relevant or there's more of it than you would have server-side. If all the data you need for your machine learning task is already in the data center, it's going to be easier just to work with it there. The second kind of criteria here is that on-device data probably should be privacy sensitive or very large in volume, because if it was non-privacy sensitive and small, you could again just transfer it to the data center and use standard techniques. And finally, we need techniques where if you're doing supervised learning, the labels can be inferred naturally from user interaction on device, or otherwise we need to use some kind of unsupervised feedback signals for the machine learning. So some good example applications, you can think of language modeling for mobile keyboards and voice recognition. I'll talk a little bit more about that. Or image classifications for, say, predicting which photos people will share. What's nice about that is that the labeling signal, whether or not a photo was shared, is naturally available on device, like I was just saying. And so over the last few years, we've started using federated learning in a large array of Google apps and services on Android, including powering smart text selection, emoji and sticker prediction in Gboard, as well as next word prediction and new vocabulary discovery, Hey Google hot word detection for the Google Assistant, as well as in Google Health Studies. And this isn't just happening. Yep, that was my Google Assistant triggering. I should have predicted that. But it's not just Google that's using these technologies. Cross-device FL is also being used at Apple and in a number of other places. So now we can start to talk about, can we come up with more of a crisp definition for what we mean by federated learning? And we took a pretty good stab at this in the Advances in Open Problems and Federated Learning work we did back in 2019. So one of the key properties is that we're looking at domains where the data is generated locally and remains decentralized. So each client stores its own data and can't read the data of other clients. So what are we going to do instead? We have focused updates that are intended for immediate aggregation, and those updates are used to achieve the learning objective. So the data is also typically not independently or identically distributed. Different users use apps and services in different ways, and so they have data from different distributions. And finally, we have a central orchestrating server or service provider that's coordinating the training, but isn't seeing the raw data. So I talked a little bit about the motivating use case of cross-device, cross-mobile phone federated learning, and that is going to be the primary focus of my talk. But there's been a lot of interest in other applications of federated learning technology, particularly in cross-silo domains. So here, instead of training models across a set of devices, we might train models across a group of hospitals or a group of businesses that want to benefit from learning a machine learning model together, but for regulatory or competitive reasons don't want to share the raw data. So this is another very interesting application of these algorithms that wasn't our primary motivation, but a lot of the same technologies and same algorithmic approaches apply. So I want you to be thinking about both cross-silo and cross-device when you hear federated learning. But because of some of the particular challenges of cross-device FL, algorithms that will work in the somewhat similar kind of always connected cross-silo domain might not work in the cross-device setting. Now I want to kind of jump into another big topic, which is privacy, and privacy for machine learning or data science in general. There's, I think, a strong perception that there's a pretty big trade-off that you have to make between privacy and utility, where utility is something like accuracy of your machine learning model. And I think the perception is that we're pretty far on the utility side of that trade-off curve, and that curve imposes a pretty hard trade-off. My view is that the situation today is actually quite a bit better than that, both because we have good technology, a lot of good controls that are already widely deployed, and also there's a lot of policy that really makes sure that strong privacy protections are in place. But certainly when it comes to machine learning, I think it is feasible to do more. And really the goal of a lot of the research that my team does is to push out that Pareto frontier of what trade-offs are possible. And in the ideal world, we can actually make it possible to achieve both more utility because it becomes responsible to access more data, as well as providing improved privacy guarantees. There's a separate set of very hard questions about kind of what's the minimum bar for privacy, or which privacy technologies should be mandated. I'm not going to talk much about that at all today, because those are questions that really require not just input from researchers and technologists, but from a much broader set of people, and often need to be tackled in a problem-specific way. But that last slide was a bit of a gross oversimplification, because privacy is not a scalar quantity. Privacy encompasses a variety of different principles. And so we've been thinking about this a lot. This isn't the only way to kind of define privacy, or to the only set of privacy principles you could write down. But we found thinking about these three principles to be very helpful in describing our technology and how different algorithms or different technological approaches address different privacy concerns. I think the single most important privacy principle is arguably around transparency, control, and also verifiability, right? People want to know how their data is being used, what you're going to do with it, what privacy protections are in place. They should have control over how their data is used. That shouldn't be just like handing you the data, and then once it's been handed over, the other party can do whatever they want with it. Privacy usually involves a certain kind of trust relationship. For example, you and your doctor, just because you give your doctor certain information shouldn't mean that they can do whatever they want with it. You're giving that information under the implicit understanding that that's intended for improving your health and well-being, but not for other purposes. So that's kind of an overall framing of privacy, but then the question becomes, what does it look like at a systems level to actually provide privacy? And there, I think that these next two principles are a little bit more operational. The first is around data minimization, and that really connects very closely to our conception of federated learning. And then the next is data anonymization, which I'll turn to in a few slides. But first, I want to explain this connection between federated learning and data minimization. And we're using data minimization here really to encompass a number of things. The idea that you should only collect the data needed for a specific computation or specific application, so focus collection. We should limit access to the data to the minimum number of people or systems at all stages, the minimum number that are necessary for achieving that kind of intended computational goal. It's also useful to, from a privacy perspective, to process each person's data as early as possible. So say aggregating or minimizing the data as soon as you can. And then we want to discard any collected or pre-processed or processed data as soon as possible. So we don't want to retain things, again, any more than is necessary for a very specific goal we want to do with that data. So a useful way to look at privacy across a system then is to ask kind of what private information might an actor learn with access to various parts of the system. So for a cross-device federated learning system, we might ask, what could someone use with physical access to the device or to the network or with root access to the server? And data minimization says we should try to limit all of these things as much as we can. And this principle is very much baked into the computational pattern of federated learning. So we want to minimize data exposure by only keeping the raw data on device, not keeping additional copies in the server. The updates that are sent to the server are going to be very focused for training a specific model. We're going to aggregate those updates together as soon as possible. And those updates are going to be anonymous. We'll strip in any kind of envelope information, any identifying information about where they came from, think IP addresses and so on, as soon as possible. And they're also ephemeral in that they're discarded as soon as possible. So these are kind of data minimization principles that are baked into almost the definition of federated learning. And of course, there's a variety of technologies we can use to strengthen those data minimization guarantees or enforce them. So for example, encryption at rest and on the wire. And there's some more sophisticated cryptographic techniques we can use to do, say, that aggregation and make sure that the server can only see the final aggregated value, the final sum of updates, for example, rather than any individual user update. I'm not going to have time to go into those technologies in detail, but if you look into federated learning and secure aggregation, you can find some good resources on that. But then as we look farther into the system, other questions arise, right? So what could somebody learn with access to the released models and metrics that are coming out of our learning or analytics system? What could device users learn with access to the final model that we deploy to end devices? And so here we want to think kind of crisply about various trust boundaries or data releases across trust boundaries. So one of the things we're increasingly working on is thinking about the whole system that's running the federated or the private computation as being in a sandbox with a minimal number, ideally nobody having direct access to, say, the intermediate states of that computation. So that the only thing that the model engineer that's actually training the federated learning model sees would be, say, the final model checkpoints and maybe metrics that go along with that, maybe from a set of different models that they were training doing hyperparameter tuning. And then there's another level of release to an even wider set of people when we deploy that model. But the data minimization principle here is to kind of release as little as possible and to hide, say, all of the intermediate state of the computation. But data minimization isn't the end of the story here. It doesn't actually fully address what can be learned from that final released output. And what we want is that the final released output of model training or an analytics task does not reveal anything unique to an individual. So whether for any kind of aggregate statistics, including model parameters, that output shouldn't vary significantly based on whether any particular user's data was included in the aggregation with a computation or not. And so this is really the fundamental principle that's at play when we ask the question, what private information might someone learn with access to those models? Now, it's worth a little aside here to talk about why this is actually important for machine learning, because it's not clear how access to machine learning model parameters in general could reveal private information. But if you think about a specific application like next word prediction in a mobile keyboard, this becomes more clear. We really don't want it to be the case that even if we train a really, really good machine learning model for next word prediction, if you type into your phone, Brendan McMahon's credit card number is, I really don't want that really good model to actually predict my credit card number, right? So those language models can be too good. So I've been using this example for a while. Actually, soon after I first used it in a public talk. This is probably complete coincidence, but this really nice XKCD came out that gets it at substantially the same point, right? That next word prediction in a generative model like that can easily reveal information that's been memorized. And these are kind of fun toy examples, but there's now a wide literature that has demonstrated that these large language models can, in fact, directly memorize training data. And this brings us to differential privacy, because differential privacy is really the gold standard for defining what it means for a machine learning model or any aggregate data to be sufficiently anonymized. And the definition is a little bit technical, but we actually don't need to worry about the details too much for this talk. But the basic idea here is that we have to do things kind of in a randomized fashion. And that if we have two kind of versions of a database that differ in some way, that the distribution of models that you get, say, when you train on that training data set, doesn't vary too much. And so there's a formula here for how we measure in terms of an epsilon and delta, exactly how similar those distributions need to be. I actually think that gets a lot of attention, and there's a bunch of alternative definitions, and proving really tight bounds of this form is kind of an important research industry. But actually what it means for the databases, the data sets to be adjacent, I think is a little bit underserved. So I want to talk about that a little bit. So this is what we sometimes call the unit of privacy. And in a lot of the machine learning research on differential privacy, the most commonly used unit of privacy is called example level privacy. And this is kind of natural. So you imagine you have two different training data sets, and they differ in a single training example. Then what differential privacy says is if I have a randomized training procedure, so typically think about introducing some noise somewhere in the training procedure in a very special way, then the distribution of models I get when I train on these two databases that differ only in a single training example, that distribution of models doesn't change very much. And therefore, if you want to take a Bayesian perspective, if you're an adversary trying to figure out whether I was training my model on D or D prime, your prior over whether I use D or D prime doesn't change very much based on observing the output of the model training. This is great for research. It's very compatible with research data sets. We have a lot of machine learning data sets that are essentially flat collection of examples. Unfortunately, for real machine learning applications, this isn't usually sufficient because in many cases, again, think about federated learning on mobile keyboard data, the same user may contribute a very large number of training examples, right? So I might type my credit card number many times. And so if the only guarantee is that if you leave out one of those times from training the model, that the model won't change very much, I'm not going to be very reassured. So what we really want with machine learning on user data is to have the unit of privacy not be an individual training example. We want the output of the model to not change very much, whether we add or remove or change all of the data from any given user, from any single user. So this is a much stronger notion of privacy, and I'll argue that in applied machine learning, it's the one we actually usually care about. The challenge here is that most research data sets don't have a notion of a user ID associated with the training data, and so it's a little bit harder to do machine learning research on this. One of the nice synergies with federated learning, though, is that federated data sets naturally do have a notion of a client or a user ID, and so they're actually very good for designing algorithms for user-level differential privacy. So before I explain how we're going to kind of add user level differential privacy to a federated learning algorithm, I need to give you kind of a skeleton of a very basic federated algorithm. And usually in federated learning, we use some variant of federated averaging, which is really just a version of stochastic gradient descent conducted locally on the devices, where occasionally we aggregate the updates from the local SGD runs. So we have a collection of devices that are selected on a given training round. They download the current model. They run some computations on their local device, say taking multiple steps of stochastic gradient descent. And then when they've done enough local training, those devices send, say, a delta to the model, the difference between their improved version of the model and the model they originally downloaded at the beginning of the round. They send those model deltas to the server, which aggregates them just by adding them. So think about adding up different gradients here. Then those get applied to the centralized global model, and then another set of devices get selected, and this iterative process repeats. And to get a formal differential privacy guarantee here, a user-level differential privacy guarantee, we really only need to make two fundamental changes to the algorithm. First, we need to bound the magnitude of any individual user's contribution. And while this might be hard in kind of centralized machine learning, it would be almost impossible if you don't know which users, which examples came from which users. Here it's pretty easy because it's baked into the federated algorithm that we compute one update based on all of one user's data. So we just take that update, and the device, before sending it to the server, clips it to have bounded L2 norm. And then the second part of the recipe is that after the server has added up all of those updates, it adds noise kind of proportional to the magnitude, the largest possible magnitude of any one update, right? So you can think about adding enough noise to mask the contribution of any one user. And that's really the kind of key idea. The analysis to turn these algorithmic kind of parameters of clipping and noise addition into a formal DP guarantee is quite complicated, but the algorithm itself is very, very easy. So this is called DP-Federated averaging, or if you do it just at the example level, it would be DP-SGD. So here's a little bit of a schematic for what this looks like and how we combine the differential privacy technology with the machine learning. So here, the way to think about it is that we're going to individually privatize the gradient or the model update for each round. So on each round, a set of devices participate. We add up their updates. We pass those into the Gaussian noise mechanism, which has a very nice DP analysis, and we get out a noisy gradient G1. And then we feed that noisy gradient into a standard stochastic gradient descent implementation on the server. It treats that average gradient or that average model update as an overall batch gradient and takes a step on the global model. And one of the beautiful things about differential privacy is it says you can do any post-processing on the output of a DP mechanism you want, and you still inherit the same DP guarantee. You can't do more computation and make something less private. So this is a really nice algorithm, but unfortunately, it turns out to be very hard to use this algorithm in a production federated learning, cross-device federated learning setting and get meaningful guarantees. And so I want to kind of step through what some of the main challenges are. And really, one of the primary challenges are, as I said, that the real secret sauce in making this practical is in the analysis of the DP guarantee you get. And it turns out the DP, the analysis that makes this algorithm practical in some settings really requires that you're sampling the devices or the training examples that participate in a particular round, that you're sampling those from a large data set. And each kind of device participates with a fixed probability exactly Q, right? So each device has kind of a small independent possibility of participating in any training round. And while you can simulate this just fine if the data is actually in a data center, This is very hard to do for a bunch of reasons in a production cross-device federated learning system. So a big factor is that devices aren't always available. We're only going to run a federated computation on a mobile device if the device is plugged in, charging, has sufficient battery already, is on an unmetered Wi-Fi network, is idle, it's not being used by the user. Basically, we want to make sure that any FL computation we runs doesn't negatively impact the user experience for the owner of the device. And so this means most of the time devices aren't available with training, which means that we can't randomly select them. Devices are only available when they decide to check into the server. It's also, it turns out, difficult to even know the active size of the population you're sampling from, and that we've done a lot of optimizations, at least on Google's cross-device FL system, to kind of maximize throughput using some custom load balancing techniques. And those, again, don't work very well with this kind of forced random sampling that's necessary for the tight privacy analysis. So, we designed an earlier feasible protocol for this, but it also would have required very complicated changes to the production infrastructure. And at the end of the day, kind of any type of amplification you get here that depends on kind of randomly picking from devices is going to depend on the pool of devices that are currently available. That is, if you need 1,000 devices to all provide updates to complete a round of training, and there's only 1,000 updates, there's only 1,000 devices available, there's no way to randomize. You have to either decide between not making progress in your training and waiting for more devices to become available, or you can use all the 1,000 devices that are available, but that's an arbitrary subset of the population. You don't have any control over it. So this challenge of applying amplification and federated learning was one of the main things we were facing. So kind of to summarize this, what we really needed to get user-level DP guarantees in a production setting was an FL protocol with a number of properties. We needed to be able to make progress on training, even if the set of devices available varies significantly with time. We need to make sure that no matter what happens, that privacy guarantee remains, even in the face of unexpected or arbitrary changes in device availability. And then there's also significant efficiency concerns. We really want client devices to be able to locally decide whether they will check into the server in order to participate in training, and make those decisions independent of other devices. And achieving this really required a pretty dramatically different approach to combining machine learning and differential privacy technology. So I'll go back to this schematic of DP-SGD, where we're individually noising the sum of gradients on each round, right? So this is great because, in some ways, because it's very simple. We just apply the Gaussian mechanism as we sum up gradients or model updates, and then we forget about the Gaussian mechanism, and we can plug those updates into whatever learning, those kind of summed noised gradients into whatever learning algorithm we want. But this is also the approach that really ties us to needing some kind of sampling argument in order to get a strong DP guarantee. For the DP-FTRL algorithm, which we developed to solve some of these problems, the key is that we're going to use a different kind of DP mechanism. Here you can see that the shape of the DP mechanism box is different. It doesn't look at each round of training independently. And in particular, that mechanism is not going to output kind of single noised estimates of individual per round updates. Instead, it's going to output differentially private estimates of the cumulative sum of all of the gradients so far. So on the first round of training, it just outputs G1, the first gradient. On the second round of training, it doesn't give you directly an estimate of G2. It gives you a privatized estimate of G1 plus G2. And then on the third round, you get a privatized estimate of G1 plus G2 plus G3. So having a DP mechanism for this different problem, for this kind of streaming cumulative sum problem, is the magic ingredient here. So that's the key idea. We want to estimate the cumulative sums. Why is this better? Well, let's imagine in the extreme case that there's only one user contributing on each round. So we're only summing up one user's update, right? So then in this DP-SGD case, we know that all of the signal in G3 is coming from a single user, right? And so that kind of gives the adversary an advantage. But if we think about DP-FTRL, yes, we have that issue on the first round, but say on the fourth round, the mechanism can kind of be clever. It's going to release some information about G4, but it can also kind of reveal a little bit of additional information about G1, G2, and G3, about all of the previous gradients. And because we're releasing a sum, those are kind of all mixed together, right? So it's hard for an adversary to know, say a particular gradient coordinate is large. Is it large because it was actually large in G4? Or maybe it was large because it was actually large in G1, but that was hidden by the noise on previous rounds. So we're giving the mechanism here a lot more flexibility. And it turns out that there exist mechanisms that can take advantage of that flexibility to give us much better privacy accuracy trade-offs without needing sampling, right? This ability to kind of mix information coming from different rounds into the output on later rounds means that we don't have to rely so much on sampling. So we can show what this looks like visually when we compare DP-SGD here in orange to DP-FTRL estimates in blue. So let me kind of walk you through this figure. Here we're imagining the true model updates always just take a step of one unit to the right. Those are shown in black, right? So if we had unnoised gradients, if we didn't pass the gradients through a DP mechanism, there would just be this continuous step from the initial randomly initialized model on the left in gray to the final model on the right. DP-SGD adds independent noise to each of those gradients, right? So we're taking kind of a randomized walk here. And because of sampling, we don't have to add a huge amount of noise on each round. And that's why you can see like the orange gradient estimates almost always move to the right. They're roughly taking you in the same direction. But because all of that noise is independent, the noise kind of builds up and kind of grows at a rate of square root of t. And we don't see that same phenomenon with DP-FTRL. With DP-FTRL, the blue model updates, the noise in the updates is much larger. I mean, in fact, in some cases, we actually step backwards in exactly the wrong direction. But nevertheless, the overall trajectory of updates, because we're correlating the noise, some of the noise on later rounds cancels out noise from earlier rounds, we actually stay closer to the true trajectory. And so another way to intuition for why this works better is that we're using more noise, but we're allowing the mechanism to correlate the noise. So the noise on later rounds can cancel out noise on earlier rounds. And so what's nice here is that in order for this to work in production, we don't need a strong sampling assumption. All we really need to know is that a single device isn't contributing too much to the model. Say it's only contributing once every 24 hours. And with that kind of assumption, we can compute the sensitivity of the overall mechanism to one user's contributions and know how to correctly calibrate the amount of noise we add. And we've successfully used this to train and launch a production Gboard next word prediction model for Spanish language. So this is a 1.3 million model recurrent neural network language model. The training took about 6 days and a total of about 2,000 rounds. And one thing I didn't really get into, but another key way to drive down the noise, since you're adding the noise to the sum, you increase your signal to noise ratio by including more devices in that sum. because the amount of noise doesn't change even if more users contribute. So we used a large number of devices participating in every round here, 6,500. We limited each device to participate at most once every 24 hours. And with this, we actually improved model quality over the previous model we trained with DP-Federated averaging. Because we weren't able to use amplification via sampling arguments, we didn't have even a formal DP guarantee for that previous model. And so the net result of this is that we were actually able to launch this model. And to our knowledge, this is the first production neural network trained directly on user data and actually announced with a formal DP guarantee. And I was really excited to be able to actually kind of make this statement. And one of the things I want to emphasize here is that we're doing this with user level DP, which is the stronger version that I've argued is what we really want in these kind of applications. And we're also doing this using a federated learning algorithm. But as far as I know, nobody had even trained a production neural network on user data in the data center, even with the weaker notion of example level DP, and kind of announced that with a formal DP guarantee. So this was a big milestone for the team, and a lot of people contributed to this across my team and many teams at Google. One of the things this whole process made me realize is I'd like to see more of this happen, and I'd like to see kind of more standardized reporting about the details of DP launches. So I'm not going to go through this in detail, but when you talk about a DP launch, there's a number of things, like before you get to the formal kind of numeric guarantee on how much certain distributions can be different, that you really want to pin down. So what's the scope of the DP guarantee? So for example, ours applies to all uses of on-device data for the training of a single model, right? We're not doing privacy accounting across training of multiple models right now. We'd like to, we're not doing that yet. What's the units of privacy? So we give, a formal kind of notion of our kind of device level privacy. We protect all of the data on any one device, and so on. There's a few other questions here which I think are important. And I just wanted to put this up briefly to give you a sense of how many different teams and people were involved in the launch. It spans kind of the core research team, federated learning infrastructure, the Gboard team, and the speech team all contributed to this. And I think I've got just a few minutes left here. So I wanted to briefly highlight some new work, which basically asks the question, can we do even better than DP-FTRL? And the answer turns out to be yes. And the key is in that big orange box for tree aggregation. And I didn't really tell you how tree aggregation worked, but roughly what it does is it builds a binary tree on the set of iterations and kind of releases information for each node in that binary tree corresponding to the sum of all of the leaves under that node, where each leaf corresponds to the gradient on a particular round. And so you can actually kind of plot the error that mechanism gives you in the prefix sum after one round or one iteration, two iterations, after 64 iterations, after 128 iterations, after 137 iterations, and so on. And that's what we see in red here. Honecker Online has to do with the particular way we kind of decode the prefix sums from the DP release. But the key takeaway from this slide is the red line is what the tree aggregation mechanism used in DP-FTRL, used in our launch, is actually doing. And you can see these really weird artifacts here, right? And there's a reason I've used a powers of 2 scale here, because this has to do exactly with the binary tree structure. But our error is very low on rounds that are exact powers of 2, but on rounds that are kind of exact powers of 2 plus 1, errors can be much higher. Or exact powers of 2 minus 1, sorry, it can be much higher. And then we hit an exact power of 2 and we get much lower error. It turns out there exist much better differentially private mechanisms for prefix sums. In particular, we propose one in this work that corresponds to the orange line here at the bottom. So it's like a 3.5x lower squared error, kind of total squared error summed across all rounds. And if you use these better mechanisms, so what's termed previous work accuracy here, this red line we were getting on a benchmark simulation data set, a little over 22% accuracy, we can get that up to over 24% accuracy using these improved techniques. I don't have time to tell you exactly how to do it, but I can kind of walk you through the thought process that got us here. So the key observation, and this was known, but that is that binary tree aggregation can actually be viewed as releasing a particular linear function of the gradient so far. That is, binary tree aggregation is really kind of a matrix. And so in this new work, I've put the link there at the bottom, we can characterize which matrices can be used in the continuous release setting with the Gaussian mechanism. It's basically all of them if you do the math carefully. And then we can ask the question, okay, binary tree aggregation is one matrix. Are there better matrices we could use for differentially private prefix sum estimation? And the answer is yes, there are. There's substantially better matrices that kind of smooth out those kind of jagged errors and produce much less total error. And so I've got a visualization of one of those kind of matrices here. So basically, this tells you kind of how much weight how much your information about previous gradients you're releasing on each round. And it makes sense that this is lower triangular. That's kind of most obvious that this mechanism can be implemented because it says on round 100, I'm only releasing some linear combination of gradients 1 through 100. I'm not releasing any information about gradients that haven't happened yet, which you obviously couldn't do. So I'm very excited about this work, and I think there's a lot more room here to continue to improve these mechanisms and understand the relationship between DP and machine learning even more deeply. So yeah, I'll end with just a couple of open questions and challenges. I mean, one I've already hinted at some new work on. Can we design better DP mechanisms, and can we kind of more directly tie those DP mechanisms to the machine learning optimization dynamics? Another kind of question on the opposite end of things, it's not really a technical question, but it's about how do we kind of communicate with users about privacy as we continue to make incremental progress, right? It's not like anything we're doing now is particularly bad, but we want to be able to continue to advance the state of the art without letting the perfect be the enemy of the good. Another big open area here is practical privacy budgeting. Here we're focused on just accounting for kind of a DP guarantee for a single model training run. But of course, we might train multiple models, maybe for different tasks, maybe for the same task. We might do hyperparameter search. It's possible to add up all of the privacy costs of those different data uses. But those privacy costs pretty quickly, I think, become unrealistically pessimistic. And aren't necessarily comparable to kind of the same numeric DP guarantee for some other mechanism. So how do we actually make this practical? And then a final direction I'll mention is here we've looked at kind of training models from scratch, because that's in some sense the simplest or purest machine learning task. But as models get bigger, and we do want to kind of calculate the total privacy cost of training lots of different models, it's going to be more beneficial to kind of share models across multiple tasks and to train models both on public and private data. So this is an area I think that's going to be increasingly important going forward. And I think I'll stop there, and hopefully we have time for a few questions. Thanks, everybody.
Thank you very much, Brendan. We have time for questions. So if anybody in the audience has questions, you can use the Q&A feature to type in your questions, and I will read them out. So while people are thinking of questions, let me start with one. So in the DP-FTRL algorithm, you're mixing information of previous gradients with the newer gradients, right? And that improves the privacy guarantees. What effect does it have on the optimization side, on the conversions? Does it does using old gradients cause staleness issues with the conversions?
Yeah, that is a great question. And one that I have a partial answer to, but I think understanding that question better is really important, especially in light of the recent work on matrix mechanisms that I talked about, because that actually gives us a very powerful toolbox for constructing DP mechanisms that kind of focus on providing accuracy exactly where the optimization procedure needs accuracy, right? So in the DP-FTRL paper, we have kind of an online learning style regret guarantee. And if you look at that, it actually says that it's actually the cumulative sum of the squared error in all of the gradient prefix sums that matter. This is one of the things that motivated kind of the FTRL view of things. You can also view the algorithm as just gradient descent, but FTRL kind of encourages you to think about things in terms of prefix sums of gradients, like the sum of all of the gradients so far. So under a relatively, I think, straightforward analysis, what that tells you is that bounding kind of the total sum of errors in those cumulative sums of gradients is the right thing to do. But I think that's because we used some relatively basic arguments, like for the online to batch conversion, we looked at taking the average of all of the iterates, right, or the as the point. And I think that result falls out of that. So I think it's very interesting to think about more sophisticated analysis and what that might tell us about how we should design our DP mechanisms.
I see. Thank you.
I have a question, sort of related to Gauri's question. I guess what type of theoretical guarantees do you have for, I mean, I haven't worked much on differential privacy other than attending talks. So what kind of theoretical guarantees do you have? And suppose it's in the form of regret bounds, for example, are there like lower bounds which sort of allow you to tell whether your algorithm is optimal or not, or what can one say?
Yeah, that's right. That's a great question. So there's a couple of different kinds of theoretical guarantees here, right? The first guarantee we care about is the actual differential privacy guarantee, right? We claim that our algorithm offers epsilon equals 9 differential privacy, epsilon equals 9, delta equals 10 to the minus something, right? Those are formal theoretical statements with a formal proof. And it's interesting, unlike in kind of proving a utility or convergence guarantee, like the constant factors in those proofs matter a ton. And so a lot of the work in kind of like, say, this matrix factorization work is about improving those constant factors, because those are the theorems. The theorems don't just give us intuition about how the algorithm should behave. Those are the theorems that say, hey, you actually have to add exactly this, at least this much random noise to your model training process, right? And so it's very much in your best interest to make those guarantees as tight as possible. In many cases, there are lower bounds for like kind of if you want to achieve a certain level of differential privacy, what's the bound on how much squared error you can have in your prefix sum estimates. Those are useful, but as I said, like there's still some looseness in the constant. So I think a lot of these things have been kind of resolved in the DP community for a while in terms of like asymptotically we understand what's going on, but we actually care a lot practically about doing better theory on the DP side that actually gets us kind of optimal constants factors. And that's what's actually really cool in this matrix mechanism work. There we can say, like, for a specific problem, like prefix sum over 512 rounds, we're actually kind of exactly optimal up to constant factors, at least with respect to a very large class of DP mechanisms.
Thanks.
We don't have any other questions. Let's wait maybe 1 minute.
Because there is somebody asking, do we have slides for public consumption? I guess we'll post the video online.
Yes, yes, yes.